So now we are working on acids and bases. I want to show you how to solve some important problems based on acids and bases. First, let us define acid ionization constant. So we'll start this by considering the generic acid-base reaction. In this type of reaction, where we have acid ionization constant, normally we have a weak acid and a weak base. So it's a weak acid and a weak base. So what does it mean? Here we have double arrow indicating that what we have here is incomplete dissociation. Incomplete dissociation. So as we can see, using double arrow means the reaction is at equilibrium. So the equilibrium constant for a weak acid and a weak base, or the equilibrium constant for a weak acid in water, is called acid ionization constant. So this is the equilibrium constant, the equilibrium constant for a weak acid in water. Now, the equilibrium constant for a weak acid in water is shown by using the expression. So let me so we use the expression Ka, that is acid ionization constant, is equal to plus A minus divided by HA. So the HA here stands for undissociated acid. This A minus stands for what we call a conjugate base, something that you read about, and this one is a hydronium ion. So the acid ionization constant is given by Ka, is equal to hydronium ion times the conjugate base, all that divided by the undissociated acid, or we can just say associated acid because it has not undergone dissociation. But this only occurs when this only occurs when a weak acid dissolves in water. So that is acid ionization constant. Let's look at another important term: amphoteric acids and bases. So these are substances that behave as both acids and bases. So one example of that is water. So water will behave as both an acid and a base, and there is a reason why I am discussing water at this point in time. So let's move on and see why understanding that water is amphoteric is important. So because water is amphoteric, it can go auto-ionization. So it can auto-ionize itself. It can make itself into different types of ions. So how do we show that? Consider this equation. If you have two water molecules, so this water molecule in liquid phase, this water molecule in liquid phase, the two water molecules will react to form, one of them forms hydronium ion and the other forms the hydroxide ion. So this process is known as the auto-ionization of water. Water is able to auto-ionize because it can behave both as an acid and as a base. So as an acid, one water molecule will donate a proton. As a base, one water molecule will accept a proton. So why is auto-ionization important? If you want to write an equilibrium constant for this, you say K is equal to H3O plus OH minus, here divided by water, or we can, if we want, you can put two waters. But take note, water is a liquid. So because it's a liquid, this one and this one become one. So down here, it is one. The reason is, since water is a solvent, it's a liquid, a solvent, its concentration does not change much. That's why we just put one there. So what it means, this equation or this expression becomes K is equal to H3O plus and OH minus. So this term is this ionization constant for the order ionization of water is given the term Kw. So it is just the ionization constant for the order ionization of water. So Kw is really important. At 25 degrees Celsius and for pure water, the concentration of the hydronium ion is 1.0 times 10 to the power 7 molar, and the concentration of the hydroxide ion is also 1.0 times 10 to the power 7 molar. So you can see that in both cases the concentration is the same. So we'll discuss the ionization or ionization of water and Kw based on these concentrations. Now, how do we do that? We said that Kw is equal to H3O plus and OH minus. But we know that at 25 degrees Celsius for pure water, the concentration of the hydronium ion is 1.0 times 10 to the negative 7 molar, and that of OH is 1.0 times 10 to the negative 7 molar. It's only when you have pure water. As a result, this Kw will be given by 1.0 times 10, 7 if you are dealing with pure water, and then 1.0 times 10 to the negative 7. So this gives a result of 1.0 times 10 to the power negative 14. So we can say that the acid product constant for the auto ionization of water is 1.0 times 10 to the power negative 14. This is an important constant, and we'll see how important this constant is. Now, when you are dealing with pure water, we say that both this and this are the same. But now when you start dealing with impure water, these will be different, and we'll see how it works, and we'll just look at the examples and see how we can use those examples to understand the auto-ionization constant, Kw. So example 1. What is the concentration of hydronium ion in a solution that is 0.00500 molar sodium hydroxide at 25 degrees Celsius? So to solve this problem, we just need to remember one thing. Kw So to solve this problem, we use Kw is given as the concentration of acid versus the concentration of base. But if you look at this solution, this is an impure aqueous solution. So this tells us that the concentration of H3O is not equal to 1.10 times to the power -7. It also tells us that the concentration of OH is not equal to 1.0 times 10 to the power -7. The reason is because we have been given here that the concentration of the sodium hydroxide is 0.00500 molar. But our aim is to find the concentration of the acid. So we are given sodium hydroxide, we need the acid. So how do we go about it? We start with our equation. Kw is the concentration of acid times the concentration of water. I mean the concentration of the hydroxide. Concentration of hydronium ion times concentration of hydroxide ion. That gives us 1.0 times 10 to the power -14. So if I can rewrite this one, I will say the concentration of acid, concentration of hydronium and concentration of hydroxide will give us 1.0 times 10 to the power -14. That is the Kw. But we already know the concentration of sodium hydroxide. It is given here. So if you want to determine the concentration of acid, the concentration of hydronium, you just need to divide here, both sides, by OH. So this part will cancel. And we'll say the concentration of the hydronium ion is 1.0 times 10 -14 minus the concentration that is given here, which is 0.00500. So it gives us the concentration of the acid as 2.00 times 10 to the power minus 12 molar. So take note that I used 3 significant figures because my question had 3 significant figures here. I did not use these significant figures because this is just a constant. Normally it's given to 2 significant figures, but I used the significant figures from the question. So this is the concentration of our hydronium ion. Let's look at another example. Let's look at another example. But before we go there, we need to define the term pH. So pH is just the negative logarithm of the concentration of hydrogen ion or the hydronium ion. That's how we define pH. So what does it mean? Because of the negative here, because of this negative, if the concentration of H3O plus increases in solution, pH decreases. So if the concentration of the hydronium ion, if the concentration of the acid part of the solution, that is the hydronium ion, if this concentration increases, the pH of that system is going to, if the concentration increases, the pH is going to decrease. Now, if the concentration of the hydronium ion decreases, then the pH is going to increase. The reason is because we have a negative here, because pH is a negative logarithm of the concentration of hydrogen. Now let's look at problems that we can solve when we know that the pH is given as negative logarithm of the concentration of hydrogen. So we'll start by solving the pH of a strong acid. Here we are asked to calculate the pH of a 0.05 molar of HCl or 0.05 molar of HNO3. The answer will just be the same because we are dealing with a strong acid. So here the calculation for this one is simple. We know that pH is given by negative logarithm of the concentration of the hydronium ion. So when you have strong acid, for strong acid, the concentration of the acid is equal to the concentration of hydronium ion. So concentration of acid is equal to concentration of the hydronium ion. So what we do in this case, we just take pH as negative log the concentration of HCl, or the concentration of HNO3. So because it's a strong acid, we just put the concentration as given there, 0.05. And the answer is 1.30. So this strong acid has a pH of 1.30. Now, how do you solve a similar problem, but now you are given a base instead of an acid? You are given a strong base and you want to determine the concentration of that strong, or you want to determine the pH of that strong base. So remember, we are determining pH. So calculate the pH of a solution that is 1.4 times 10 to the power negative 5 molar sodium hydroxide. So you need to show if this solution is basic or acidic. So here we need to take note that we are given a base. We are not given an acid. So the way to solve this, we can solve it using two methods. The first method is to understand that Kw is equal to H3O plus, then OH minus. So since we have a strong base, here, the concentration of the base will be equal to the concentration of the hydronium ion. So what we are going to do is, here where there is hydronium ion here, we'll replace it with the given concentration. So we can say the concentration of the acid, because we want to calculate pH, which means we need to determine the concentration of the acid, although we are given the concentration of the base. So the concentration of the acid is given by Kw divided by the concentration of the base. And we know that Kw is 1.0 times 10 to the power negative 14. And the concentration of the base is given 1.4 times 10 to the power negative 5. And when we do our calculation, we find that the concentration of the acid is 7.1 times 10 to the power negative 10 molar. So we can say that our hydronium ion is equal to 7.1 times 10 to the power negative 10 molar. Now, we know that pH is given by minus log so this one will be equal to negative log 7.1 times 10 to the power negative 10, which gives us 7.00. Not 7.00 though. So let me do the calculation again. That's a wrong answer there. Negative log 7.1 times 10 to the power 10. Yeah, it gives us a pH of 9.15. So let me just get rid of this. So the pH is 9.15. Take note, when reporting pH, we change the number of significant figures that we are given to decimal points. So we change the number of significant figures that we are given in the problem to the number of decimal points. For example, here you are given 2 significant figures. So our answer will be to 2 decimal points. So when determining pH, when calculating pH, change the number of significant figures from your problem to the decimal places, in your solution or in your final answer. So in this case, what we have done is to check that this one has 2 significant figures. Therefore, the answer must have 2 decimal points when you are calculating the pH. Really, the reason is because we are moving from a value to a logarithm of the value. So that's important to take note. So that's how we deal with the the pH problems. When you are dealing with a strong base and a strong acid, you should be able to determine the pH. Also, you should be able to determine the concentration of the acid or concentration of the base. Thank you.